This paper addresses the problem of robust deep single-image reflection removal against adversarial attacks. Current deep learning-based SIRR methods have shown significant performance degradation due to unnoticeable distortions and perturbations on input images. For a comprehensive robustness study, we first conduct diverse adversarial attacks specifically for the SIRR problem, that is towards different attacking targets and regions. Then we propose a robust SIRR model, which integrates the cross-scale attention module, the multi-scale fusion module, and the adversarial image discriminator. By exploiting the multi-scale mechanism, the model narrows the gap between features from clean and adversarial images. The image discriminator adaptively distinguishes clean or noisy inputs, and thus further gains reliable robustness. Extensive experiments on several datasets demonstrate that our model remarkably improves the robustness of SIRR across disparate scenes. For the SIRR problem, a captured image I is typically formulated as a linear addition of a transmission layer T and a reflection layer R. Alpha means reflection weighting. We first investigate the robustness of deep SIRR methods. We apply the widely used and powerful attack method PGD to generate adversarial samples. For completeness of the robustness evaluation, we present various attack modes by referring. Specifically, we employ different attack objectives mean squared error and learned perceptual image patch similarity, as well as different attack regions, the full image region, the reflection region, and the non-reflection region. Through a systematic analysis, the most effective attack mode and currently the most robust SIRR model are identified. Then we conduct adversarial training based on this model to enhance its robustness. As the perturbation level increases, the output quality degrades clearly. In some cases, for example HG21, the PSNR has halved from 20 to 10 when epsilon equals 8. The visualization results are more intuitive. For HG21, the perturbed input image, A, has no visual difference from the original input image, but the prediction result, C, is totally corrupted compared to the original prediction, B. These results indicate that the attack method is effective in terms of various attack regions and different attack objectives. Although all methods show similar degradation trends against adversarial attacks, there are still differences with respect to attack modes. Besides, existing models show relatively superior or inferior robustness. On the other hand, it is observed that the MSE attack shows sharper decreasing trends than the LPIPS attack. In terms of attack regions, we notice that attack on the full region, the first row, or non-reflection region, the last row, is much more stable than on reflection regions, the middle row. SIRR models natively consider reflection regions as distortions and aim to remove the reflection effects. Perturbations on reflection regions may be judged to be reflection itself, which makes attacks on these regions much harder. The overall architecture of the proposed network is illustrated here. It consists of a cross-scale image encoding stream, a multi-scale feature decoding stream, and an adversarial image discriminator controlling 3 dynamic convolution modules. A blended image is first downsampled to its 1/2 scale and its 1/4 scale. Then using the cross-scale attention module, multi-input images are gradually taken into the encoding stream to obtain multi-scale deep features. Afterward, the decoding stream exploits multi-scale fusion modules to aggregate these feature maps to recover the output transmission images. Based on the perturbations of the input image, the adversarial image discriminator generates the weights to compute dynamic convolution kernels. Hence, the main network could be adversarially aware, and it is able to adaptively handle clean and corrupted inputs. Our model is mainly motivated by the robustness consideration. Inspired by previous research on visual attacks and defenses, there are 3 key ideas for robustness enhancement. The first idea aims at the multi-scale image processing strategy, which has been verified as robust against adversarial attacks. The second idea is to use transformer blocks as feature extractors. The third idea comes from the adversarial examples detection strategy, which learns to distinguish normal and adversarial samples. The quantitative results of the baseline and our method are reported here. Without adversarial training, our method gets better PSNR and SSIM on clean images. Yet, under the MSE or LPIPS attack, the performance of our model decreases more significantly than WY19. Taking PSNR on the nature dataset as an example, our method outperforms the baseline. This indicates the robustness improvement, and our method predicts the output more steadily. According to testing results, our method shows great robustness over WY19 on the nature and real dataset. The degradation of our method is more significant on the SIR dataset. But the absolute metric values are much higher than WY19. This is the results of attacking on the full region. The left column is the original blended image and the ground truth transmission image. Subfigures A, B, and C are perturbed input images. The output of inputting the original image, and the output of inputting the perturbed images, respectively. Here are more results. This is the results of attacking on the reflection region.